This panel has been fun to assemble. I expect that we're going to learn a lot from it, but I'm going to let Mr. Jim Reuter tell you about how he set up the panel and introduce all of his panelists. Jim is the Associate Administrator for the Space Technology Mission Directorate. I've worked with Jim for many years at Marshall and at headquarters, and he's always been a thoughtful leader. Jim, happy to have you here, and I'll let you introduce your panel.
Yeah, thank you, Chris. And it's a pleasure for us to be here. I'm really excited about being the last panel. And like Chris said, that does mean that we're the only thing between us and lunch. And so we know there's that interest, but it also is, this has been, I think, a really excellent 3 days of discussions and panels and presentations, and we're really glad to culminate it because we're the ones that look forward. And so now here, as we end this year, we want to look forward, but we want to build on the things that are before us. And so, just over the last couple of days, the Moon to Mars panel discussion with Marshall Smith, the lunar landers this morning with Jay and company, and Artemis 1 and 2 update was really fascinating with Mike. And so our intent then is to look at those technologies that will help enable Moon and then on to Mars for space exploration. And could I have the first chart? Yeah, okay. So I'm not going to talk in any detail right now, but what I did want to talk about is we have 3 primary objectives as we're going forward in terms of the exploration campaign. The first thing is to, as we've been talking about and as Mike just talked about, was boots on the ground by 2024. Enable the first woman and next man to go surface. The next, and so there's critical technologies that we're working on, and even the lunar panel talked about several of those that we're working with them on collectively. But also, if it's not something that's substantially far along, it's not going to get on that mission. But the next step then is a sustainable presence on the Moon by 2028. And for there's sustainability means a couple of different things. One, it can be that we've enabled surface operations, whether it be by the U.S., whether by another international agency, or especially by commercial and stuff. And another part of that, and a real key to this, is that we're looking forward to Mars and utilizing this campaign to help us get to Mars. And so just on this chart, the idea is that we have proving grounds, really, both LEO ISS area as well as the Moon. Things like life support works well there. Precision landing has avoidance is something that works well as a proving ground. In-space manufacturing on low Earth orbit. Operations, just learning to operate and stuff, and something in simulating a mission to Mars, as well as lunar surface technologies. And we'll be talking about several of those things here. But there's also then, and so there's a number of those items represented on this chart that kind of go through Moon and on to Mars. But we're also talking about things, there are also items that in order to enable Mars that are unique for that. Landing heavy payloads is a real key one. The advanced in-space transportation system, atmosphere RSU, that sort of thing. So just from an overall framework, that's the things I wanted to talk about. But now I want to introduce the panel, which I think is a really excellent panel. We're privileged to have them here. And I'll just go through and introduce them, and then they'll talk about each of their own particular areas of insights in this overall campaign. First, to my direct left is Steve Altemus, the President and CEO of Intuitive Machines for the last 5 years. Does it feel like it's been that long?
Longer.
Especially lately, maybe. Anyways, his company's been solving significant challenges across multiple industries, aerospace, energy, providing intelligent and autonomous systems, complex computational modeling, simulation, and so on. And before that, Steve has had a very distinguished NASA career, including Deputy Center Director and Engineering Director at JSC. And I would say he's truly visionary, one of the best people at Broad Thinking that I've known.
Thank you, Jim.
Next to Steve then is Robyn Gatens. She's the Deputy Director of the International Space Station Division in the Human Exploration and Operations Mission Directorate at NASA headquarters. We're all here to help. In addition, she's the agency's systems capability lead for environmental control and life support systems, leading a team of subject matter experts in that area. She's a true expert in human systems. and we hope that she'll discuss some of her particular challenges in her area. Then next is Niki Werkheiser. She's the lead for our Lunar, what we call, and she'll introduce a Lunar Surface Innovation Initiative in our mission directorate. Niki brings just a wealth of experience to managing complex projects across NASA centers, industry partners, academia. She's really been the thrust behind the development and implementation of in-space manufacturing on ISS efforts, and implementing novel on-demand manufacturing, repair, recycling capabilities, and feeding forward to the exploration missions. She spent most of her career doing payload development, both at shuttle and ISS. So she's going to talk more and focus on lunar surface systems while we're here. And what I would say is that she's probably, if I could coin a term, the best collaborative leverager that I know. There's a story behind that. But and then finally, Wanda Sigur has over 38 years of aerospace experience in program management and engineering. She recently retired, relatively recently, retired from Lockheed Martin. Everything's relative, I guess, as Vice President and General Manager of Civil Space Business, where she had executive responsibility for, well, really, at all levels. Planetary, solar, astrophysical, Earth remote sensing. And she currently serves as a consultant with particular focus on helping startup space companies achieve their missions. She's actually also our chair. We have in Space Technology Mission Directorate a advisory group for us. It's called the Space Technology Industry Government University Roundtable, or Sigur. And that's comprised of senior experts across industry, other government agencies, and academia, and provide us advice and insights as we go forward. It's a great group. We meet a couple times a year with them and really enjoy it. And I've had the pleasure of working with Wanda in a few different roles over the years, and she's one of the best in the business. So with that, I'll turn it over to Steve.
Well, thank you, Jim. Thanks for
And
having
go
me
to
on
the
the
next
panel.
charts, please.
And thanks to AAS for having us today. Let's see if we can get our charts up. There we go. Let's see if we go next one here. Advance. That works. So I was having dinner with a few folks, various ages, the other night, and we were all talking about Mars, or we're talking about why we came to the agency to begin our careers. I came in the late 80s and had an idea of going to Mars. And then the person to my left was talking about, hey, I came in the 90s and I came to go to Mars. And then the next person comes in and says, who's sitting across the table, says, hey, I came in 2000, I was promised we were going to go to Mars. So I think the critical thing here that I wanted to talk about versus technologies was that the human Mars missions have been right around the corner, it appears, for decades, and yet it's been elusive for some reason. And that is because the technology buy down on the NASA roadmap has been very difficult. So how might we think about buying down the technology risks on the exploration roadmap in a concerted way to make meaningful progress? You know, for years we've been studying challenges associated that are laid out as technology risks on the roadmap. We've been doing ground demos, but it's very difficult to get those over the finish line and mature the technology readiness level to where you're confident in those components and subsystems and systems to take it to Mars, right? So, you know, you think about in-flight demos and you say, well, mainline programs can't on-ramp major technology changes in systems, components and systems, because they have their primary mission to do. So they're not necessarily going to buy off on taking on additional technology challenges based on cost and schedule challenges. So it's going to take this agency a focused, concerted effort to buy down the risk on the roadmap. It's not about redefining the roadmap, it's about accomplishing and buying down the risk and raising the TRL level of the component systems and subsystems on the roadmap. I think we can make, like I said, incremental and meaningful progress against the roadmap by combining two things. One is a more exploiting every opportunity for in-space, in-flight demonstrations of technology to buy the risk down. And the second one is to use these newer, more innovative procurement techniques and commercial business models together to lower the cost and the time to effect some of those in-flight demonstrations. So every program should be responsible for some set of exploration risk buy down in each program. It doesn't have to be integrated into the mainline program, but can be added. And I'll give you some examples of how we're doing that on our program, which is the Commercial Lunar Payload System program with NASA, or Intuitive Machines Lunar program. So here's an example, right? So we chose as a company to pursue liquid oxygen and liquid methane propulsion. That's been, oxygen and methane propulsion has been on the roadmap for decades. It calls for it's high ISP, no toxicity, it's space storable, it leads to surface utilization, or ISRU, yet there's no spaceflight heritage. So when are we going to take the step forward to actually fly in space LOX methane? So Intuitive Machines has done that and proposed that on our Nova C lander, and it'll be the first methane in space engine. First use of cryogenic propellants for a planetary lander. And it has heritage to NASA efforts that have gone on for years in LOX methane research and demonstrations on the ground. So we're taking a stepwise, basic approach, low-risk approach to the first engine and the first propulsion system. We have conservative ISP. You know, we're down around the 320 ISP, not striving for the unattainable right out of the gate. Minimal cryofluid management, thermal control, just because we have such a short mission. But there's an opportunity to burn down this cryopropellant risks in this first mission and share that data back with NASA so that we can evolve. And so this is an example of how one flight in one program can start to buy down that in-space risk. And if you look at the Intuitive Machines Lunar program, and it's the anchor tenant is really the CLIPS program within NASA, over several missions, we'll be attacking not only the cryofluid management problem and the LOX methane propulsion problem, but we're looking at precision landing and hazard avoidance and visual processing units and visual navigation, retiring those risks and building more robust systems there. And then as you move forward into the later missions, you can think about things like putting in a baseline laser communications and actually doing return samples from the moon and cargo resupply. So this back to what Jim indicated about operations and cadence. This one program in NASA with one small business like Intuitive Machines is looking at attacking the risks on the roadmap and contributing towards getting us to Mars eventually. So that's kind of the source of the topic I'd like to talk about today. Thank you, Jim.
Thanks. Robyn?
Thanks, Steve. Well, you were singing my song about focused efforts to advance things on the roadmap. That's what NASA's capability teams were really set up to do. And so I represent the capability team that's responsible for life support and crew health systems. So I'll be talking a little bit about that. There we go. So the scope of my capability team, which is really designed to identify capability gaps, draw the roadmaps to get those gaps filled, but then really advocate across the agency for that funding, for those focused efforts to really mature and close these capability gaps. And a lot of what we do is integrate. You know, there are already great projects going on by the different agency investments, but I run up and down the hall going, if you do this piece and you do this piece and I fill in this gap, together we can collectively close these gaps and really move things forward. And we're starting to make that progress. So my area includes life support, environmental monitoring, fire safety, and logistics reduction. And then I recently absorbed the crew health and performance scope, which includes, you heard Lindsay Etchison talk yesterday about the spacesuit. There's all kinds of EVA physiology that goes along with designing that spacesuit. What is the crew going to do? What kind of work are they going to do? How is their performance affected by the suit design? we look at that. Radiation protection, monitoring exercise, human health countermeasures, so exercise equipment, the food system, which is a huge capability gap between what we have today on space station and what we're going to have to do to go to Mars, and then the medical equipment. So all of these areas have gaps between where we are today with our state-of-the-art system on space station and where we need to be to do these missions to the moon and Mars, and we're focused on closing those gaps. So our strategy and challenge is a really continuum between things that we're already doing today in LEO and in ground test, and then taking those technology development efforts and infusing them into the Gateway program, the Lunar Surface program, and then on to Mars. So along the way, we're trying to address different challenges. In LEO today, we're adding new capabilities to these systems and also really focused on improving the reliability of our existing capabilities, and using the ISS as a primary test bed because it's a permanently crewed platform, it's a microgravity environment, and it's relatively easy to, if something fails, get something launched and keep learning. Over the course of the space station, we have successfully reduced the uncertainty associated with system failures to the point where we've reduced the amount of spares we would have taken to Mars by several tons. If we had tried to do that mission at the beginning of space station versus today, we've really brought that uncertainty down. We still have a long way to go. If we were to take the systems on space station today to Mars, we'd still have to take a prohibitive amount of spares in order to ensure a successful mission. So that is a key aspect of what we're trying to do in LEO. And because it takes us a long time to reduce that uncertainty and prove the reliability of our system beyond the horizon of the space station, we're going to continue to need test bed in low Earth orbit. And we're looking to purchase that as a service from commercial providers that are going to take over with habitable platforms in LEO after the space station. You heard Doug Comstock's talk yesterday at lunch. He talked about that plan. And that's one of the services that NASA hopes to purchase. So we're going to leverage that to keep our test bed going in low Earth orbit. Not only will it serve as a fleet leader, but it'll allow us to have a test bed to keep infusing new technologies as they come along. I don't think I would ever send a technology to Mars without first testing it in low Earth orbit. And then from there, we're going to infuse those technologies into our missions, our Artemis missions, and some new challenges we're going to have to address there. Dormancy. We're going to have uncrewed periods that we don't have today on space station, where we leave systems dirty and have to, our water system, and have to come back and restart it. We're obviously going to have reduced logistics supply and ways of getting rid of trash, autonomy. While we have these uncrewed periods, the vehicle is going to have to operate autonomously. And then when we get to the surface, we're going to need to deal with dust mitigation. And that's a new challenge we haven't had to deal with on space station. And then, obviously I can't go back. I'll just say, when we go to Mars, that's where this robustness really plays in. We're going to need the system to last for a 1,000-day mission. We're going to have to, when we shut the door and the crew is inside, what they have is what they have. So we're going to have to really be reliant on that system. And then we're trying to get to additional loop closure. Today on space station, we have about 50% recycling of our air that we get back, and about 90% recycling of our water. And we're trying to increase that so we can obviously reduce consumables. But I would take the less recycling over, or more reliability over less recycling, I can always launch more consumables if I know my system's going to last. So we're making progress. I'm happy to report. We've got roadmaps. We're well on the way to executing these roadmaps. We are evolving the system we have on Space Station today into the system we need to execute these missions. And so here's a few highlights. We launched one of 3 planned carbon dioxide removal demonstrations, new technologies to the space station earlier this year, the thermal amine scrubber, and we've got more coming. And we'll test them on orbit and then do a down select among those and hope to take the winner and infuse it out in the gateway. Our brine processor assembly, today we throw away the concentrated leftover, what we call brine, that's left over after we process urine. And we lose about 10% of our water in that brine today. So in order to close our loop further, we've developed a brine processor assembly with our commercial partner Paragon. And I'm really excited because last week they completed a significant test milestone and achieved their dewatering performance and actually exceeded it. So when we fly this to space station next year and plug it into our water system, that we're going to increase our water recovery from 90% to 99% and essentially close that capability gap. So that's really exciting. We've got our universal waste management system, also known as our toilet, and that's also flying next year. Today we have a Russian toilet on the space station, so we're going to fly a U.S. toilet. And last year, the image on the right is a double toilet stall that's going to house that U.S. toilet next to the Russian toilet in Node 3 on the space station. So we had to launch the stall to get ready for the toilet. And that'll, by the way, support the additional crew that are coming with the commercial crew program. In fire safety, we've been doing a number of study the fire demonstrations, large fire experiments on the Sapphire test series, and then coming up on Sapphire 4, 5, and 6, which fly on our Cygnus vehicle, we're going to include detection and post-fire cleanup technologies in those. So we're excited to see how those perform. In environmental monitoring, we're moving towards a suite of capabilities that allow us to monitor all the aspects of the air and water and environment on board so that we don't have to rely on sample return to the Earth. So today, the picture of Kate Rubin's there, we've sequenced DNA for the first time on board space station, and that's going to lead to a microbial monitor that's going to be able to identify and quantify species in our air and water without the crew having to do culture-based methods and plate count, which is the method they have to use today. We also have flown a particulate aerosol sampler that's leading to particulate monitoring technology. That's going to be important when we do these missions where we are bringing dust back into the environment, where it's going to be important to measure particulates for respiratory hazards. And then we recently launched the spacecraft atmosphere monitor. This is going to monitor the major constituents of the atmosphere as well as trace gases. And then on the right there is our radiation monitor that's on board station and will be flying on Orion. And then in crew health and performance, we're working on miniature exercise devices. Today on space station we have a big treadmill and a big resistive device and a bicycle. And we can't fly all that on our smaller exploration spacecraft. So we have to miniaturize exercise devices, but that are also effective in maintaining crew health and performance. So we've got 2, one from the European Space Agency and one from the U.S. that are about to undergo testing, and we're going to down select among those 2 and fly the winner to the space station. And then we've got, Lindsay already talked about the suits. We've got work going on in the advanced suits and also the food system. You've probably seen pictures of the veggie We're quite a ways away from taking veggie to a crop production facility or a crop production capability where the crew can grow things, pick them, eat them, replant, and it's sustainable. So that's what we really need to move towards. And that's my last slide. So with that, I'll turn it over to Niki. Thank you.
Okay, the first thing is I'm going to apologize for my crackly voice, but those familiar with North Alabama know that allergy season never ends. So I am thrilled to be here today to talk to you about the new Lunar Surface Innovation Initiative, and I believe this is probably our first public discussion, so I'm even more excited to be able to share what I know. First thing I want to say is, so STMD, the Space Technology Mission Directorate, has the very exciting role, I find it very exciting, of developing and performing demonstrations for the primary technology hurdles that we can retire in order to get to the key capabilities and really move forward to larger scale systems. So of course we can continue scaling up those systems with some engineering development, but the idea is that we can actually have no to very little work required for the primary technologies for those key capability areas. So the LSII, the Lunar Surface Innovation Initiative, was established to focus on that integrated system of what I'm going to refer to as lunar surface infrastructure key capabilities, identify those, develop the kind of key roadmaps on how we start with our very earliest missions, working closely with SMD, for example, on CLIPS, to start proving out these technologies and build a very deliberate step function up to our larger pilot systems. So we'll be kicking that off formally in FY20. Of course, there's already a lot of work underway in the area of lunar surface development. Our key roles and responsibilities are, of course, ensuring that we have a very ambitious, we make sure to use that word first because it is ambitious, and that's what makes this exciting. Cohesive, because we have a lot of stakeholders. We work very closely across the STMD programs, which I'll talk about, as well as our counterparts in HEO and the Science Mission Directorate. And I'll talk a good bit, as Jim mentioned, that I love collaborative leveraging. And this is an area, fortunately, where we can really work closely with industry and academia and our other government agencies to effectively and efficiently develop these capabilities. So what I want to talk about today is kind of the 6 primary, as I mentioned, lunar infrastructure capabilities that we're working to develop. The first of those, we've talked a little, Steve mentioned, is very important, is in situ resource utilization. Sustainable power, obviously, on the surface, having a distributed network and making sure that we're scaling up to meet the integrated power capabilities that we need to have. Extreme access, that includes things like surface mobility and, of course, communication, especially the larger, smaller autonomous rovers, which helps to inform the HEO pressurized rovers that are being developed. Surface excavation and construction, lunar dust mitigation, which Robyn referred to, and these are things that, of course, we have to worry about the first day out of the gate, and we're going to study on early CLIPS missions as well as our very first human missions in 2024, and how do we mitigate things like dust when we're looking at our landers and our optics and our HABs. And then, of course, extreme environments. How do we survive lunar night? We've got a good bit of effort going on in these areas with materials and TRL maturation to make sure that we can meet the needs in the lunar environment. So as you can see, this is quite a robust portfolio. It's one that requires ample coordination and integration, not only within the agency and across the spectrum that we've discussed, but with industry and academia. As we've all heard through this symposium, that is an absolutely critical aspect of what we're doing to meet the timeline and the ambitious objectives we have, and personally, I think one of the most exciting parts of what we're doing. So not only within STMD, of course, do we leverage our prizes and challenges. For example, you might know about the Centennial Challenge that we wrapped up last year for 3D printed habitats on surfaces using Regulus simulants. We also have SBIRs, which we use extensively, public-private partnerships, the NASA Advanced Concepts. I think I just heard earlier from Astrobotic, we have one we just awarded as a phase 3 for exploring lunar pits. So a lot of exciting work there to be done. This is a large task, and you can see a very integrated task when we look at how we approach this for missions. So we have also initiated an effort with a university-affiliated research center, Johns Hopkins Applied Physics Labs. In this initial task, they're looking at what the model would look like for them to be a system integrator, a UARC to serve as a system integrator across the Lunar Surface Innovation Initiative areas. This would include industry, academia, other government agencies, and of course our NASA experts. A fundamental aspect of what we're looking at there is how we would set up a lunar surface consortium that would consist of the parties I just mentioned, where we can actually work very closely together to examine and discuss, for example, the roadmaps that we're laying out in each of these areas from start to finish, and then how we could actually do very novel collaborations and acquisitions working with these stakeholders. So I'm very excited about that. We've got that up and running. We've been working very hard behind the scenes in a multitude of these areas across those platforms. ISRU, for example, we have started already developing the first technology demonstration that would be able to fly on an early CLIPS mission, and we'd be able to turn the hardware over toward the end of calendar year 20, leveraging some work that Honeybee Robotics has done through Resource Prospector with a mass spectrometer. They've got a coring drill and an auger drill, and looking at how we can integrate that and get that up quickly to start getting that very kind of fundamental foundational knowledge in the earliest missions possible. That will then, of course, not only inform our technology development moving forward, but also science, operations, our processes. So I think there'll be a lot of exciting lessons learned early on that we'll build on and continue iterating and incorporating into the roadmaps with all of our stakeholders. With that said, I'm probably going to stop there because I want to leave a lot of time for questions, and I know everyone's getting hungry, and I look forward to dialogue.
All right, thanks, Niki. Thanks for the opportunity. The conference seems to be a great way for everyone to catch up and to focus on the amazing time that we have to work in the industry at this time. So congratulations on the successes that we've had so far. So as far as framing goes, the phrase proving ground was introduced in the mid-2010s. I think it was introduced in 2015 as a means to discuss how LEO, how the moon would be used as a means to pathfind and demonstrate technologies that are critical for more Mars exploration. So my intention is not necessarily to go over all the same technologies. We've had days and years, actually, of discussing progress and forward steps, but to highlight those things that I think are game changers, potentially. So first of all, the journey and surface exploration. I think we all know that there's an intention to test like you fly and to do a full vetting of every bit of hardware that we intend to send to Mars. But I will remind those of you that have a few years in the industry that it's never a conversation or dialogue around architecture and big hardware. It's about the little things. It's about the test. It's about the sensor. It's about a glitch in software that keeps us from being able to launch or execute or perform. So having said that, early architecture definition of what we're planning to do on Mars is going to be critical for us to understand what some of the details are so that we can actually demonstrate that hardware around the moon. I flagged a few technology areas, specifically pulling for those elements of logistics that I think are potential game changers. As both Niki and Robyn have said, NASA's got a pretty good shopping list of the kinds of things that they'd like to emphasize and grow, but I do think power, propulsion, and comms can make a huge difference. Any major improvements in those areas will effectively change our vision of what it will take to get to Mars. So within this 10-year window or so, as we're getting smart about the moon and we're landing on the moon, a vision towards how we get smarter on not just the hardware, but these new technologies. And I'm thinking specifically nuclear technologies. I do want to flag nuclear because it's a little different, and it's probably not politically correct to say so, but there is an opportunity for the moon to be a nuclear test bed. Not with terraforming or anything along those lines, but as you consider that, there are probably opportunities for us to test reactors in an environment that is not on the Earth. There are some considerations for how we might want to make much more rapid progress by taking advantage of the lunar areas. NASA has identified key areas for future technologies and have identified partners in pushing forward. And they have identified advanced comms and EDL and in-space manufacturing and assembly and advanced materials, but I wanted to highlight a few more. Thermal management, we've talked a little bit about cryo. Steve flagged that that's going to be an important element as we consider ISRU, but an emphasis on temperature extremes and thermal management will be key. Simulation will be important. One of the things, well, I'll ask, how many folks in here are program managers and have been program managers? You know that there are probably a few key things and probably two things that can make the biggest difference in success. One is managing time and certainly cost, but a consideration of how much time you have to resolve an issue makes all the difference in the world in whether or not you're going to be successful. If you can imagine living the 1,000 days in the closed capsule, to borrow Robyn's imagery, decisions have to be made quickly. They have to be correct. Being able to simulate and resolve issues and challenges and know what the right answer is almost immediately will be absolutely critical. So certainly artificial intelligence and rapid virtual system trade capabilities will be critical. I wanted to flag servicing. Refuelability, reusability, something that considers the fact that we're not talking about a once and done mission, but a forever mission, requires that we have a capability to demonstrate how we refuel and reuse all the hardware that we plan to put in place. So again, I wanted to flag those. Certainly crew health is absolutely critical, and there are a number of efforts that are being done at LEO that can help make that a much better understood and higher performance area. But having said all those things that are associated with, I think, the challenges that we know, I did want to foot stomp a couple of additional areas. So Earth independence is a thing. We don't really have our head around that just yet. We talk about ISRU, but there are more areas. To the extent possible, Earth independence has to be demonstrated at the moon. Besides the things that have been mentioned so far, build and space technologies, I think, are something that we probably should spend a little bit more time on. As you consider 3D printing, certainly there are certain advances that have been made in structural components, but the additional work that's being done in 3D printing food, there's some conversation about 3D printing bones. Reusing every bit of the stuff that you're taking with you has to be part of the criteria of how you live and sustain yourself without access to anything else. Biosystems on a chip, something that allows for folks, again, to do virtual modeling to figure out what quick answers need to be once they're posed with problems that have never been imagined before folks took off on this long journey. The last thing I did want to talk about is probably going to sound a little bit like it's got solutions in policy and strategy, which is the concept of sustaining public interest. This journey to Mars, once we get beyond the moon, and probably including a bit of the moon, will take at least 20 years. Estimates have come in at $1.5 to $5 trillion. And I think those of us who've been around for a while recognize that that's a whole lot of money. Number one, it's going to be more than any budget that NASA has. And it's going to be much, much longer than 7 to 8 year increments that are associated with presidential administrations. So we have had some trouble, I think, in probably very recent years in recognizing that a shifted focus can cause us to lose ground and perhaps deter us from this overall course. There are some exceptions. Efforts that are buoyed by national commitment obviously have been successful. We've been recently celebrating the Apollo program, where some folks say that it was a presidential statement that made it possible, and the challenge to get to the moon, certainly geopolitical elements and other things were big drivers. But it was also flagged that it wasn't just President Kennedy stating that we're going to go to the moon, because most every president after that has had some space objective or goal. But some have said that it's President Kennedy's assassination that kept America focused on being able to make that his legacy. I think all of us are probably aware that there are a few missions of Apollo. Once the lunar vision had been established, there were a few missions of Apollo that were canceled because of other priorities. We need to maintain a focus such that America, as well as the world, wants to stay completely engaged. And even though it feels that a lot of those solutions may feel like policy, I think that there are some technology challenges that could also be addressed. Success efforts include the space station, which I think has been buoyed not just by its forward progress, but by international collaboration. Privately funded efforts have also been able to bridge those gaps of presidential concerns. We have quite a bit of support and technology that's actually flowing out of the work that's being done by SpaceX and now Blue Origin. And it's a model that's been used by other programs. The B-17 bomber, for example, was primarily funded by private dollars before it was picked up for major government investment. But there's more. Aligning the journey to Mars with national needs and the comms campaign necessary to keep American interest, I think it's got to be something we talk about. How do we marry the things that we're trying to do at the moon, things that we absolutely have to do to get to Mars, with things that folks find of interest and are necessary? I think needs to be part of the dialogue. This concept of Earth analogs is not something that we've really explored, but I think it's something that we need to consider if we're really focused on bipartisan support and funding. NASA's space forming project provides a good example. NASA partnered with the Center for the Utilization of Biological Engineering in Space and commissioned a space forming project. Long story short, there is a $10 billion industry attracting interest from Silicon Valley and around the world. The initial Starhopper, SpaceX's Starhopper, set up a business plan which not only took advantage of the work that had been done with DCX to give us a technical capability, but it also put forward a plan to promise point-to-point transfer on Earth, capable of sending massive payloads into orbit and humans to the moon and Mars, but also scores of passengers around the world in periods of half an hour. So all of these become potential ways for us to consider what the next technology campaigns look like. And again, there are some elements of policy and acquisition that would allow for us to continue to maintain support and interest, but I think it needs to be part of the overall technology challenge. So I've got a few samples in this chart, but the only one that I'll flag in the interest of time is actually the last one, which is the sustained interest. Examples of some things that could be of immediate interest would be perhaps to take the work that's being done for habitats on the moon, and as we eventually get them to habitats on Mars and tie them to perhaps a homelessness campaign, or not to create more homeless folks, but to provide a solution that folks might find of interest and would be therefore looking to NASA and the space industry to resolve their issues. The last point I guess I'll end on is actually a comedy bit that was done by Wanda Sykes. She has a bit that she does on space where she describes NASA as a welfare program for really smart people, where they are so smart that the only thing that you can think to tell them is to go in the corner and look up. I think there's obviously some reconnection that we need to do as we're considering this longer-term 20-year effort and generating the interest and dollars necessary to pull this off.
All right. Do we have time for questions?
So, questions? Do we have an appetite for questions? Here's one.
Thank you very much for your presentation. This question may be directed towards Robyn with regard to the space environment. So as we look at the solar cycle 25 may be waning in about the mid-2030s. So as we look to being on Mars, the galactic cosmic rays will be of more influence and their higher energy levels. So what is being done to plan for that?
Right, so that's one of the big human risks that's being tracked by our human research program and all of the research that they're doing. And galactic cosmic rays is one of those, we can shield for solar particles, but the GCR is a particular challenge. So going when it's low, going faster seem to be, the main ways to mitigate those concerns, as well as trying our best to shield.
All right. Thank you. Appreciating all of the interest in developing technologies to prepare for humans to have a sustained presence in space. Are there technology investments planned for instrumenting the effect on the human system on the Orion flight, on the Artemis flight? I think that this relates a bit to the question that was asked earlier as to whether or not there's going to be some form of android with pressure sensors and temperature sensors and other instrumentation to really characterize the impact on a human through that flight path.
Well, I know that there are radiation sensors being carried to determine the radiation environment, as well as, I'm not sure what else. I don't know if someone...
There certainly are going to be a number of environmental strain gauges and stuff that
Okay.
will...
So I have one for Wanda. There has been a bit of a decline in the number of papers presented at AIAA conferences and other conferences in just propulsion and propulsion research. Not just nuclear thermal and solar electric, but in liquid and solid propulsion. Do we see that we're going to, and there's not very much on your technology sample up here, do we see a change in that in the future that the academic community can get involved with?
Papers follow research, follow funding. So as we're considering what technology objectives and goals we would like to have for Mars, certainly that dialogue probably starts with the NASA and others in the technical community, whether it's the DARPA or AFRL, where they identify what the targets and goals are. A few years ago, there was a big campaign to look at evolving chemical propulsion systems and considering hybrid systems and other things for deep space exploration. So certainly as there is that greater interest and there are dollars that are put out there to say, what are your concepts, and here's an opportunity for you to drive down the TRL risks, then that would certainly, I think, generate the research that drives the papers.
So thinking about lunch, is there, as the greenhouses progress into like actually productive, self-sustained food sources, is there any thought to reusing excess biomass from that, or even growing other things like soy that could be processed into plastics or hemp or cotton or anything like that?
Yeah, I'm glad you brought that up. That's one of our biggest challenge areas, I think, is the food system. Today we rely on mostly prepackaged food. For space station, they get a variety of fresh food with every cargo flight, but it's definitely not self-reliant. And so when we think about going to Mars, the food system has to, not only if we send prepackaged food, it has to maintain its nutritional viability for the duration of the mission, which is a challenge, or we have to have a way to introduce nutrients as we go. And that's where the crop production facility that we're developing is going to play an important role in introducing that fresh food. The challenge we've seen, obviously, there's hydroponics and all kinds of research going on the ground, but adapting that to microgravity is the challenge. Getting the water to the plant roots, and then what do you do with that biomass? So you can harvest, and you've got all the roots left behind. You've got to somehow regenerate and replant without having to carry massively heavy new soil and seeds, which is what we send today. We'll send up pillows that already have the growing media in it. So that's the focus of the roadmap that we've been putting together, and some initiatives that we've been starting to try to work with our industry partners who are doing terrestrial applications of these things, but try to adapt them for use in microgravity.
And I'll add to that from a technology perspective, in addition to the things that Robyn mentioned, STMP also has SynBio or BioManufacturing, where we're looking at how we can grow things like stem cells. One of the companies on space station that has actually a bioprinter right now, TechShot, that they've been testing with cardiac cells. They're also working with terrestrial companies that use stem cells and are evolving how to actually, quote unquote, print food, different foods, meat, and different types of yummy edible materials that are also other options in addition to the areas that Robyn's talking about. So there's a lot of technology development that could not only impact how we do business in space, but could have huge impact here on the ground as well.
Go ahead, Frank.
I was somewhat surprised to not hear any mention of mobility for the astronauts such as rovers. Does anyone want to make a comment on that?
I mentioned it. It was just really quick. I can talk about it for a long time, though. Yeah, so that's important. And in our very early missions, we're actually developing the small autonomous rovers and to test those out. Those are in development. HEO, of course, this will help to inform their pressurized human-scale rovers that they're working, and I'll let Robyn talk more about that. But there's certainly definitely awareness and roadmaps that we formulated on how we're going to build to get to the full range of mobility requirements and capabilities that we need.
Any others?
Right here.
So going back to the food question, since it's close to
Everyone
lunch.
must be hungry.
Yeah, it's lunchtime.
On Earth, about a third of our waste is bio. And composting is done here on Earth and can reduce the waste stream quite adequately. Are there any technologies in terms of composting and actually using, you're talking about reprocessing, regrowing, but actually turning it into compostable material that you can grow from?
Niki's shaking her head. I'm going to let her take
So
this one. I'm not sure.
That same synthetic biology group at Ames and JSC and across several different centers actually are, we've done some experimentation. I was, as Jim mentioned, working some of the 3D printing previously. We had a project, and there's a lot of terrestrial development in the area of taking, plant waste, for example, and using the cellulose byproduct to actually print or manufacture with. So we're definitely looking at different ways that we can kind of do that in a cyclical manner. That we're using, the idea, right, is that there's no waste, that we can use everything and see everything around us as a potential resource or even feedstock potentially. So those are definitely some areas that, as we mentioned earlier, I think are important to work with industry and academia. And we are working at NASA to define what our capability needs are, the applications, how we would use those things, and then work very openly with industry and academia to develop those.
And I will add that we do have research institutes for a variety of topics, one of which is led by Berkeley for us. That's about manufacturing in space. That's kind of looking at some of those things. And then complementary to that, we have a Centennial Challenge that's gotten underway in terms of CO2 processing anaerobically.
And that was the one that Wanda had mentioned that's really stimulating quite the economy in Silicon Valley, the Cubes Institute. Yeah.
So we're not going to serve until 12:30, so you might as well ask a question. But in the meantime, I'll ask Steve a question. Wayne Hale made a very nice comment at the last session, and he's so eloquent, I will not try to repeat it. But it goes along the lines of what is the sharing between the commercial entities? If we're going to have a lunar economy, one of the things that Wayne talked about is sharing failures, problems, issues. What about technologies across? How do you feel about sharing with your competitors?
Yeah, that's a great question and topic of discussion, right? I think it begins at the government level, thinking about government-funded programs and what are the data rights embedded in those programs, and that thinking has been evolving over the recent few years within NASA in a favorable direction that gives the business, commercial business, a competitive advantage to make their own investments, right? If you have your data, you can make your own investments to kind of create a market for yourself, right? Because exclusivity drives the markets, drives your commercial competitiveness. So I think that's a step forward where the government can manage data rights, where you know they have march-in rights, but maybe they can give some benefit to industry to make a competitive business. On the other side, though, on the commercial side, we propose things like open source licensing and open source tools and software and even appliances, so that you can build a consortium around a specific topic where today everybody's building something custom and you don't have a standard in the industry that you can go to, and so the costs of the mission are so much higher because everything's built custom. If you can build these appliances in a standard and share it with the community, we can all benefit by flying more missions, not necessarily making money on the unit itself or the appliance itself, but actually approving another mission to fly, right? So I think there's a lot of good examples out there where there's university-backed consortium, communities of practice that industry can participate in, that develop IP that's shared around with everything. If you look at, there's an example in the gaming industry, the Unreal Engine that does gaming processing. That model is tremendous. It has moved exponentially as soon as they opened it up to the community to share in the advances that everybody contributes to. So I think those kinds of practices are the things that are going to buy down the cost of in-flight demonstrations and buy down the cost of future missions. We all have to get along. We have to share a little bit. Right?
So, Jim, any final comments?
Let's see. No, I think we really appreciate the chance to have been able to talk here. We appreciate the participation and the questions. And I think it was I really especially want to thank each of the panel members for your excellent commentary.
All right, thank you.